So it's a pleasure to hear today Gourab Ghatak. He's a former PhD student of in Telecom Paris, and he has done his PhD in Grenoble with the CEA. And now he's assistant professor in IIT Delhi. Before you were in IIT Delhi, so you lose one eye, I think. And let's say he acquired some expertise and in stochastic geometry applied to wireless networks. So I let him the floor.
Thank you for inviting me and for having me here today. Yes, as Maso said, I'm from IIT Delhi. Just one slide on what it is. It's an institute in the northern part of India. It's a big institute. Even our department, which is electrical engineering, is quite big. It has 65 faculty members, and it's organized into 5 groups of computer technology, which works on AI and ML, communications and signal processing, of which I am a part, integrated electronic circuits, power, control, and automation. So all aspects of electrical engineering, basically. In the department, we have more than 400 PhD students currently, and several master students. In the QS rankings of the department, we are currently at the 49th position. That's about it. These are the overall areas that I work on. There are 2 aspects. One is on stochastic geometry and the other is on online learning bandit algorithms. In both, we focus on theory and applications likewise. In stochastic geometry theory, currently we are exploring novel line processes, which a part of which is going to be presented by me today. The other is on clustered hardcore processes, especially to model Wi-Fi networks where the access points are following hardcore processes, but the users are clusters around the parent points, which are hardcore processes. We use some kind of stochastic geometry tools for analyzing vehicular communications and industrial IoT networks. In industrial IoT networks, we work on age of information, where to place intelligent surfaces in an indoor environment which is of metallic in nature. In vehicular communications, we are doing some spatiotemporal analysis of movement in using both stochastic geometry as well as time series analysis. In bandits, we work on some kind of theory which is online change detection, sequential change detection, whether actively or based on some past statistics and so on, best time identification problem, and the applications of that are on risk averse algorithmic trading and so on and so forth. This current work is jointly with my PhD student, who is currently a PhD student in IIT Delhi, Taha, a former master's student, Soradeep, who is working with Continental now. He is working on automotive radars for them currently. Professor Martin Haenggi, who is from Notre Dame. Right. The references of this talk can be found in these 3 papers. The first one, where we introduce this new line process called the binomial line process. The second one we recently presented is how to use those line process and the underlying or the developed Cox process on top of that for wireless networks. The third one, which actually kind of brings all of them together with the meta distribution analysis as well, is currently under revision, but this can be found online. There are 5 parts to the talk. I'll set the context very quickly, give a brief history of line processes, we'll introduce what the binomial line process is, and try to motivate that why it should be also an interesting line process to consider to model modern wireless networks. Built on the binomial line process, we'll introduce the binomial line Cox process, which is the doubly stochastic process driven by the binomial line process. And finally, we, as an application, we discuss the meta distribution of SINR, where the access points are deployed according to the binomial line Cox process. Okay, so very quickly, I think I don't need to introduce stochastic geometry, but I still have a couple of slides of introduction. First of all, we have to accept a fact that we are going to talk about models, and there will be questions on why this model is correct, which model is more correct, which model is less correct, and so on and so forth. But some of the models can be useful to derive some insights which are otherwise very computationally intensive to derive, and so on and so forth. In the beginning of my trip, I was in Eurecom. I used OpenCell ID to discover how many base stations are there around. They're quite, so in both these places, this is in Paris, it's near the Eiffel Tower. How many base stations a user is able to discover. So the colors represent the type of base stations. The blue one are LTE base stations. The orange ones are UMTS, 3G base stations, and there are 2G base stations somewhere as well. Both of them have the same area, right? And different number of base stations deployed on the same area. The question is that the network insights that you derive from one part of this or one of these scenarios is quite different than the insights and the optimization that you do for another part of this scenario. The question is whether we study these two scenarios separately, optimize as a case-by-case basis, or consider them as realizations of an underlying stochastic process with probably changing parameters. So this is another example where, again, the blue larger circle is the area where this blue smaller circle, the user, is able to discover base stations. In both cases, it is able to discover 9 base stations. So these are 2 different locations in Delhi. But empirically, we found out, so the part of this talk is sponsored by a company who is an automotive company in India. So they were interested to know that how the same number of base stations around a user can lead to different kind of experiences as the user is traveling. So you see that in both cases, this user is able to discover around 9 base stations. This is just outside of our campus. The base stations are around this street, which is called the Outer Ring Road. It's a big street. Here it's a bit more uniform, but if you focus on, I mean, it's a bit unclear now, but these base stations are also around or very near to these the larger streets, maybe except these two, all are near the larger 2 streets present here. So if a user is present uniformly in this area, which you think about an indoor user, so these places are actually buildings, residential places. That kind of user, which is uniformly distributed here and versus uniformly distributed there, will have different experiences as compared to a vehicular user who is only present along the streets of a city. So what, as it turned out, a vehicular user has a much better experience in this kind of a network because in all the realizations, it was only present in all the instances, it was only present along the outer ring road and probabilistically closer to a base station. As compared to here, where the roads can actually go everywhere, but an indoor user had a much better experience here because there is more uniform distributions of the base stations. As a result, in stochastic geometry, we do not study these individual instances separately. Instead, we create realizations of virtually infinite realizations of network and try to answer statistical questions of user performance across the network. So you can think about it as a simulation accelerator where you have same kind of trends which you can derive instead of having rigorous system level simulations. Okay, so the motivation of line processes is the new generation deployment of wireless networks, which is along the top of lampposts or tagged on top of lampposts along the streets of a city. There are several examples. For example, New York City has deployed such small cells which are on top of lampposts, focusing on high-speed connectivity for pedestrian users. In South Korea, Taiwan, in Sacramento, in San Jose, I have an example from San Jose as well, where they deployed millimeter wave base stations along the streets of a city on top of lampposts. So deployment is along the streets, but not only that, coverage is along the streets as well. So for example, you think about so this is a millimeter wave small cell in San Jose. The green one represents the location of the small cell. The blue crosses represent the places where the receiver was able to correctly decode the control channel. So you see that you can be very far from the base station and still be in coverage, or not be in outage. You can be also very near to this base station and still be in outage. Because of the structure of the streets and the buildings around it. So you can be behind the building and hence no coverage, but you can be in line of sight. So the classical idea that the farther you go from the base station, the lower and lower likely you are to get a good coverage is true, but not, I mean, there is a bit more nuance to it because of the structure of roads. You can see that the coverage reaches here, the streets create a waveguide like phenomenon. So the coverage actually reaches you even if there is an open space for the signals to travel. Other such examples where the streets, the models that we develop for streets can be useful are movement of vehicular nodes. So vehicles always move along the streets. Autonomous robot movements, for example, inspecting underground pipelines, movement in warehouses, large warehouses. You can think about autonomous robots which are going for some kind of housekeeping functions or doing inventory. So they move along straight lines. Underground metro or railway system or network of rivers, etc., can all be categorized or studied under this model called line processes, which we will be discussing. I'll explain what line process is. It's one of the candidates. Roughly, it's a collection of lines in a Euclidean space. We look back at some of the history of these line processes, what they are and how they came into being. A part of this history is taken from Professor Dillon's talk, at least until here. I've added these two on top of that and some things there. So line processes, fundamental properties can be traced back to around 64, a bit before that as well. But Poisson line process, we'll discuss what that is. The fundamental properties were developed, then spectral analysis was done. Properties of stationary line process as a general framework for line, more generalized version of line processes. Then it was extended to random lines in hyperbolic planes. Mosaic processes, again, generalization of lines in larger dimensions, network of rivers. Francois' paper was big. I think it was the first one which does Poisson line process for modeling street systems for analyzing wireless networks. Then there was a lot of activity. I'm sure I missed a lot of in this curve, but the part that I would want to focus on is this one where it was used to study wired systems and then wireless systems in 2012, the introduction of Cox processes. Then an exhaustive study of Poisson line processes was done around 2018 to 2020 when Professor Dillon, his group, they published a book on this as well. Interestingly, I'll talk briefly about this, which is the L1 distance measure in a Manhattan line Cox process, which means we deal with distances where you are allowed to only move along the streets. So this is also something we'll discuss. Professor Haenggi's group said that these models are not accurate enough to model the actual reality of streets, and hence they came up with more accurate models. And in this line of work, we'll introduce one more line process and claim that it to be even more accurate than before. Just feel free to stop me at any time during the talk. We don't need to wait for the end of the talk. Okay. So there are candidate models for emulating streets. So a Voronoi tessellation, you drop Poisson points on a plane, and you draw the coverage boundaries or the cell boundaries, and you call them the streets. This is a bit tractable, but there are more tractable models. And this is the dual graph of that. So you join the points of the Poisson point process, and you get the Poisson delunator triangulation. This Professor Haenggi's group said that is a bit more accurate. It's Poisson-Lilly pond model in which you drop the Poisson points, choose a random orientation of the line, and let them grow as long as they hit another line. You stop there, and then you get this structure. It has a bit more accuracy. If you look at the data of real streets, it's a bit more difficult to characterize as compared to Poisson line process. They also did Poisson stick process. Again, Poisson points, you drop them, and each one has a mark, which is the orientation and the length of the sticks. And then you have a union of them. The Manhattan line process is like a Poisson line process. So Poisson line process, I'll discuss a bit later what they are. Manhattan line process, you only allow them to be having an orientation of 0 degree or 90 degree. Yeah. All these processes are homogeneous processes. So you go anywhere in the plane, you study the statistics of these lines or the properties of these lines, they remain the same everywhere. So they are motion invariant. You can study these kind of networks which are built on these line processes from the perspective of a single point, we call that the origin. However, from the perspective of a city, the streets are inhomogeneous. So streets are characterized typically by city planners as kilometers of streets per square kilometer of area, right? So in this quantity, how much length of streets you have per square kilometer of area, it changes as you move along the city. So it's more dense in the city center. You have a lot of crossings, you have a lot of streets. As you move to the suburban areas, you have fewer and fewer streets. And two cities far off are generally joined by one single street, or we call that the highway. Now, if you want to find out how the property of your wireless system or any kind of system that you have optimized varies, how its properties varies across as it moves from the city center to the suburbs and then to another city, you have to take into account this kind of inhomogeneity in these line processes. For example, you think about channel access protocol. So let's say that the operator has deployed one base station per 100 meters along the streets of a city. It has done this throughout the extent of the city. However, the MAC protocols that you have developed, how frequently you should access a channel, how many people would access a channel together, etc., would be very different at the city center because so many streets intersect, and hence, as we saw, there would be more interference because of the line of sight coverage and so on. As you move farther from the city center, although along that street it has the same deployment density, which means it has one base station per 100 meters, but just because there are now fewer intersecting streets, you will have a different optimization parameter, or the value of the optimization parameter that you are trying to do. You want to answer questions which are, let's say, not wireless networks perspective. So for example, in villages, you are interested in where is my nearest highway so that I can get to my nearest bus stop. If you are driving, you are interested in where is my nearest electric vehicle charging point. So it depends. So if you are very far from the city, the only hope you have for the nearest electrical vehicle charging point is on your street, possibly because there are not much intersections. But if you are at the city center, you have the possibility to jump to other streets through the intersections. So again, to answer questions like this, you have to take into account the context, whether you are at the city center or the outside, or how far from the outside. This attempt has been made several times to model non-homogeneous streets. So this is by Orange Labs. So this is, I think, map of Lyon, where they said that, okay, the same observation, you are very near to the city center, it's more dense. As you move out, you will have rarer and rarer streets and their intersections and so on. So as a result, what you can do is do some kind of data-driven approach. So you try to measure how many streets are there, how much kilometers of streets there are per unit area, and you try to find out the appropriate parameter value of your model of choice, whether it's Poisson line tessellation or Voronoi tessellation, which one ever maps the best. The motivation for this talk is to introduce one line process, which will take care of this gradual decrease of density in a single model without tuning these parameters too much. Which brings us to the binomial line process. We'll introduce what a line process is. So a line in a Euclidean plane can be characterized by two parameters. The distance this line, the red thing is the line. The distance that it has with the origin is r, and the angle that normal makes with the x-axis theta. These two parameters uniquely determines what a line is. Now these two parameters can be mapped in a representation space of theta and r. So a point in the representation space represents a line in the Euclidean plane. If you have a set of points here, it will represent a set of lines in the Euclidean plane. If you have a Poisson point process here, what you will have there is a Poisson line process. Instead, we have a very simple construction. I think out of the all line process construction, this is the most simple one to explain, is that you do not have the representation space infinite, which means in this half cylinder, you do not keep this half cylinder to have infinite range in plus and minus directions. By the way, you can have 0 to r and 0 to 2 pi as well. Instead, you can have 0 to pi and minus r to r. Instead, you bound it and say that my points can be generated only within minus r and plus r. It can have any angle. And the second thing you do is fix the number of points. So as a result, what you will have is a binomial point process in this set, in this generating domain, right? And the line process corresponding to it would be the binomial line process, right? So basically, we have all the points of Euclidean plane xy which follow this linear equation such that the parameters are driven from that generating set is the binomial line process. We will call this D, where these are generated, these two parameters, as the generating set of the domain set of this line, and a point corresponding to a line as the generating point of that line. And these generating points form a binomial point process in the domain. So if we look at the instances, we have something like this. So this is an example with 10 lines generated within, I think, 100 distance or 100 radius from the city center. And this is a realization of a Poisson line process, an instance conditioned on 10 lines. And this is an instance of a Poisson line process, which has the same density as number of points divided by pi into 100 square here. So if you zoom in further and further into this area, you will probably have structures something like this. But what our claim is that if you want to, without parsing your entire road network into different locations with different metric values, if you want to have a very a quicker global picture of how a let's say a vehicle's performance would be as it starts from the center of Paris and moves towards Lyon, you will try to have this kind of a line process as a representation of that. As it moves along the line, as it moves away from the city center, parameterized on how far it is from the city center, it will have a certain experience, which is now characterized by this line process instead of this, which is homogeneous everywhere. I think the construction is fairly simple. You can.
So you have the maximal distance to the origin is the same in all cases, right? You just change the number.
In this one?
Yeah, I'm trying to parse. I mean, so R is the distance, maximum distance to the origin.
Yeah, in the binomial line process.
Binomial line process, right? And
here you can generate anywhere.
Okay. Okay. So B and C are
Poisson line process.
Are the Poisson line process? You mean the isotropic one?
Yeah.
Okay.
So all are isotropic from the perspective of the center on the origin. So it's a rotation invariant.
Okay. Well, the other two are translation invariant.
Yes.
Right. Okay. So and your point is that A is a better representation for this density stronger in
the center,
closer to the center, and more sparse outside.
Yeah.
Yes, and in C you have the same density as in the city center in A.
Yeah.
Okay.
Yeah, throughout.
Okay.
So it's non-homogeneous. It's a non-stationary process. The statistics of this line process cannot be now characterized from the perspective of a single typical point, for example, the origin, but it's isotropic. Its properties can be seen from any point, depends on its distance from the origin and not the orientation. Think about a city like Paris. Talking about 100 meters from Paris, any direction, you probably have the similar kind of statistics. So without loss of generality, let us consider this. Let's not call it the typical point, but let's call it the test point. The test point is located at the x-axis at a distance of r0 from the center. So it's this guy. We try to now find out interesting properties of this binomial line process. So let's say we want to find out the distance distribution to the nearest line from your test point. So if the nearest line is at a distance of t, that means there are no lines crossing this green circle, which is at a distance of t. These lines cannot be generated everywhere. They are only generated within the red circle. By the way, one thing. So the points, the generating points are forming a binomial point process in the representation space. They are not a binomial point process in the circle. if they were a binomial point process in the circle, that would mean that the distances or the location of the generating points are uniform here. Rather, we keep the distances uniform, so that the distance of the line from the center is uniform. Within the green circle, there are supposed to be, we want to find out the void probability that there are no lines passing. So we see that at any angle theta, there is a range of r. If a line is generated, it will cross this green circle. We try to find out the range at which it becomes the tangent, beyond which, if the line is generated, it will not cross this green circle. If we map all of that in our representation space from 0 to pi, we get this kind of structures. It looks like this because it's cosine of something. For a Poisson line process, it's not clipped because Poisson line process lines could be generated anywhere in the plane. In the previous example, we see that for r, for a given theta, we find out the minimum and maximum value of r, where if a point is generated, it will cross that green circle. And hence, in the representation space, we have these structures which we call domain bands, where if a generating point is within that band, it will create a line in the Euclidean plane which intersects that green circle. So if you want to find out the probability that no points intersect that green circle, we just want to find out the probability that no points lie in this domain band. So basically, we find out the area of this domain band. It's different for different values of t, and increases and decreases as t and r0 increases. I'll not go into the details of this. This is the area of the domain band explicitly calculated. If your test point is, so let's say, in the city center, which means your test point plus the distance which you are interested in is less than the generating distance of the city center of the lines, then you have a constant area of the domain band, and then it changes as you move out. Using this, we find out the void probability and the distance distribution. So 1 minus the area of the domain band divided by the area of the generating set raised to the power the number of lines which are fixed now, it's not a random variable anymore, is the void probability. And 1 minus the void probability gives you the distance distribution to the nearest line. The second thing that we characterize is the metric that we started with, which the city planners generally use, is the line length density, kilometers of street per square kilometer of area. For that, we first define the line length measure, which is the expected value of the L1 norm of the line process with a subset of the R2, the expected value of it multiplied by NB, which is now fixed, right? And if this is the line length measure, in the limiting case, if we take concentric circles or annuluses, right? And we find out the line length density of these annuluses as the width of the annulus goes to 0, we get back what is the line length density. We integrate the line length density to get back the line length measure, right? You see that this line length density is some constant until this r for this model, and it decreases. It decreases as 1 by r as r goes to r grows higher. So you have two parameters of interest here: number of streets and where they are generated, which means how many streets are sanctioned by your city administration, and what is the area that you are calling the city center. So in this model, if you want to, if you want to fit this model into a certain street network, you control these two parameters to say that, okay, within the city center, I have same density of streets more or less, and it decreases as I go outside of the city center. This is a representation of how we derive the line length measure. So we have annuluses, and then they go to 0, and in the limiting case, we have the line length density. We also have the intersection density, which is interesting because the number of accidents also grow with the number of intersections. And also now the reconfigurable intelligent surfaces are being deployed in the intersection so that you have more line of sight coverage. The intersection density varies as square of the intensity of the Poisson point process for a Poisson line process. For the binomial line process, we also have the similar structure of being constant until the number of intersections that you can hope to encounter remains constant until a certain distance, and then it decreases. I mean, something like this. Okay, so what do we have done until now is characterize the line length density as well as the density of intersections, which remain constant, and then decreases as order of 1 by r as r increases. Some results are skipped, for example, distance to the nearest intersection. This also depends on where you are located. So let's say you want to reach your nearest intersection to maybe get to the nearest bus stop. This also decreases as you move away from the city center. Now, on top of this, we define the doubly stochastic process, which is the line-Cox process. So on each line of this binomial line process, we define an independent one-dimensional Poisson point process with intensity lambda. We will call the union of this 1D Poisson point process as the line-Cox process. So we have these lines, and on top of them, we have a Poisson point process. Each are 1D PPP, and the collection of this is the binomial line-Cox process.
That's a question.
Mm-hmm.
So, in view of your density arguments, would it make sense that you again find something which is not homogeneous on the line, with more users close to the center and decreasing density far away from the center for the structure on the line?
Yeah, you mean the points on the lines?
Yeah, right. Say you could take an intensity which decreases with a distance to the origin and in whatever way, right?
Absolutely. So that's an add-on feature which you can introduce. Mm-hmm. So the first point is that even if you start with a homogeneous points, you will end up with less number of points in an area because the lines are decreasing. And on top of that, you can have decreasing number of points as well, which will make him doubly decrease or something. Yes.
If you compare to Glohagen works, she has, you cited her before, she has studied the history of how cities have been built and so on to derive models and so on. How do you compare with this? Because what you show is the fact that you have a good model that is quite simple in the sense that it is tractable. Mm-hmm. And that is inhomogeneous, so it's interesting to model cities. But how do you compare to real data and to the works of Glohagen, for example? Mm-hmm.
So this is something which we are currently doing. So we have another department called TRIP in our institute, which study which is a road safety department. So they have a lot of data which they have collected on these type of metrics, how wide and narrow the streets are, how dense they are, how many intersections there, and so on and so forth. Now we are currently investigating. So of course, as always, the correct answer would be a mix of many models accurately represents the street. I think the crux would be based on the system that you are studying, which are the aspects that you keep, which are the aspects that you remove, and so on. But to answer your question, we have not done it yet to claim that this is more accurate or that is more accurate. I mean, for sure that theirs are more tested with.
And another remark is the fact that, okay, you can control the size of the city center, but can you also control the decreasing function? I mean, the way it is decreasing should be probably adapted to every city. So
adapted to
different cities. Yeah. For example, you may have a very dense city center and then decreasing very fast. I don't know. But in Paris, maybe it's slower, or I don't know. So, do you have a parameter on this?
So no, because the model parameters become a constant to this function.
Yeah.
Right, NB and R. So your decrease is sine inverse of 1 by R. This is a bit fixed.
Something you cannot control.
Yeah. What you can have is some R, capital R, which is a function of small r, if it makes sense. It will, so intuitively it means that this is more city center, that is less city center, and things like that. So you can generate some points, more points inside.
You could generalize your domain by having several thresholds, for example, R1, R2, and different maybe densities in every box.
Yeah. So that will become a discrete version of that.
Kind of discrete.
You can have a continuous
one. That the density is decreasing continuously, smoothly.
Yeah, this is the next target to compare with. Okay. So if you are interested in decreasing density of streets, why not have a Poisson line process with an intensity which is decreasing with the distance? Yeah. So there are some kind of lines which are generated in those models which are not very useful to us. So you have possibility of one road suddenly being present very far. Rather, what we were trying to model is that if you have a different, and these are kind of going to different cities, right? And in the decreasing intensity Poisson line process, you'll suddenly have a street like this, which of course makes sense because you can have other streets. Yes, but then that might not be the an important feature of studying just this city. Let's say you think about a vehicular radar, right? How it should adapt its beam width as it is moving away. So we are just interested in what's happening here and as it goes on to this stretch of highway, right? But you're right. In when we are talking about only modeling streets, maybe
to compare to real data because maybe you have some peripheric or
yeah, I agree. Okay, so we have where was I? Yeah.
Because are you convinced when you come up with a new model, it's always difficult to convince people because they have their habits and so on. And they don't want why a new model. You have to convince me that it is better and so on. So when you submitted your papers and so on, you didn't have problems like this to convince people that this model is interesting for some reason.
We had, and that's why the paper is in the revision stage for now, 9 months.
Okay, so I can imagine.
So as long as it was only about studying lines on the plane, which was the first paper, it was okay. But then when we said that, okay, this model is good for streets and we study wireless networks on it, then there is a problem. So okay, if we want to find out the nearest BLCP point, we can now allow the lines to cross my circle. So let's say we are interested in whether there are points within this green circle or not. So they form a chord. Now the chords cannot have any points. Okay, you can form chords. You cannot form chords at all. That way you don't have points, but you can form chords and not have points as well. So you find out the chord length of each of these lines, which are generated in this red circle that makes in the green circle, and we find out the void probability accordingly. So you have a chord length and a void probability of the Poisson point process in that chord length. And then you find out in the domain where they are generated such that they make the chords and raise it to the power the number of lines that you have. This gives the distance distribution to the nearest BLCP point. From a wireless network perspective, these are locations. If the locations are modeled as point of BLCP, the above result characterizes the distance distribution to the nearest access point. This is a bit interesting because you have fixed number of points. Now, from the palm perspective, if you condition the location of the point, condition a point being on a certain location, it is not only that point, but necessarily a line passes through that point. The others, unlike the Poisson point process, now you have NB-1 lines, which become a part of the new binomial line process, consisting of one reduced line, right? It's a minor problem. It makes calculations a bit more complicated, but it's important nonetheless. It's necessary to characterize the statistics because on an event such that a transmitter is located on a given point, which means a receiver associates with the transmitter located at X, then these interfering access points are located not only in the NB-1 other lines, but also on the line necessarily passing through X. Right? It's statistically closer if you think so, because otherwise it could have been anywhere. The probability generating functional, it helps us to derive product of expected value of product of point functions. For example, you can have given pollution sources and diffusion models, what is the expected intensity of this is something which is good for writing to grant proposals now in Delhi. And given base station powers, what is the received power, what is the stochastic charge locations, and so on and so forth. This is for the Poisson point process. For a binomial line process or binomial line Cox process, it's a bit complicated because a line intersects. So if let's say my nearest point is at D1, from my test point, my nearest point is at D1. So a line intersects the circle with the center as the test user and the radius as D1 only if its parameters r and theta have follow this inequation, right? Otherwise, it doesn't intersect. So as a result, for all the intersecting points or intersecting lines, if you try to find out the part of that conditional probability generating functional, it's that function evaluated over all the points where the lines are generated, but they do not create points which are within that D1. So you have to integrate from this distance to infinity for those kind of lines. But for the lines which are not intersecting at all, you can generate points everywhere, right? Yeah.
What is the f inside?
So f is any point function that you're trying to evaluate over this Cox process. So you want to evaluate function at the locations of the points, but now in the first case, the locations of the points need to be away from D1. That means that the lines, if they are intersecting, they cannot have points generated inside that circle of radius D1 in that center. But the lines which are not intersecting, they can be everywhere. So this is an example of a point function. So this part is the PGFL of a Poisson point process, which is b to the power minus lambda, integral of 1 minus the function, so on and so forth. And this one, you integrate over the location where you intersect, the domain band. And this one, you integrate across the location, which is the representation space minus the domain band. So as a result, the line containing the nearest point intersects almost surely, whereas the other lines may or may not intersect. So we have three parts to the PGFL. One represents the line which has my nearest point, so it definitely intersects, almost surely intersects. And then there are other lines which may or may not intersect. Right. Okay. So what did we characterize? Distance to the nearest street as we move from the city center. Distance to the nearest node, example bus stop, charging points, etc. Scaling of this density of streets and intersection as we move away from the city center. Probability generating functional, and currently we are actually trying to see which is the model or how good this model is or something. Now we look at an application. We move to the second part of the talk. So I hope meta distribution is something which we are familiar with. So there is again few slides of introduction if needed. It's mostly taken from Martin's blog, so it should be okay. And if somebody was not listening to the talk until now, this might be a good time to come back. So let's talk about a random variable z. Expected value of z or the mean of z is good, useful, but it does not give us a complete picture of z. Right? So hence we introduce a little z to compare it against with the larger z, the capital Z. And we form this family of random variables, which we ask the indicator that whether capital Z is greater than small z or little z or not, right? Now, if we take the mean of these random variables instead of Z directly, this means the family of this mean gives us the distribution of Z. Now, this is more interesting because it tells us that if Z does not depend on any other randomness, this provides a complete characterization of Z, which is to say that the CDF or the complementary CDF here gives us a complete picture of a random variable, right? The probability of any event, if you're interested in whether Z is between values A and B, it can be calculated by manipulating these elementary members of this family of expected value of indicator random. However, if Z is a function of other sources of randomness, then this does not reveal how the statistics of Z depends on this individual random elements. Okay. For example, if Z is a function of two random variables, for the moment, let's take them as independent, X and Y. Then to find out how X and Y individually impact Z, we need to add one more parameter, that's a little x, and we talk about the meta distribution, which is the expected value of that family that we were talking about, but conditioned on one of the random variables. We now ask that the indicator of this random variable, whether it's greater than x, little x or not. Now this family now gives us the meta distribution. A better way to write it is this. Don't know whether better or not, but more intuitive. The probability of capital Z being greater than little z, we're not interested in this. We're interested in a bit more nuanced features, which is probability of z being greater than little z for a given value of y, which now is a random variable because of y. We are asking whether this random variable, or we are asking about the distribution of this random variable instead of the mean of that. Hence, the meta distribution is defined by first conditioning on a part of the randomness. It has two parameters. The distribution has one parameter. The mean has no parameters. Right. So we can go back and forth. We start from the meta distribution. If we integrate it with respect to the little x, we get back the distribution. We integrate the distribution, we get back the mean, and vice versa. Right. Okay. So basically, you have this random variable. The mean of this gives us the distribution, whereas the distribution of this gives us the meta distribution. An example, so let's consider two exponential random variables, x and y. Z is x by y. The mean, the CDF directly gives us this. It's a parameter on Z, where mu y is 1 minus lambda x, mu y is 1 by lambda y. That's how you define the exponential, sometimes by mu, sometimes by 1 by mu. The meta distribution now depends on little x and little z. Now, why this is useful? We take another example where you have two realizations of a Poisson point process. You put users on the grids, the location of the grids, wherever the grids cross, and you talk about whether these users are in coverage or not, while considering two types of randomness. First, the distances. So you take any user, the distance to its nearest base station is random. And also you have the received power, which due to fading is also exponentially distributed. So as a result, we'll say that the received power is x by y, where y controls where the distances are and x controls where what your fading parameter is. Right. Now, if we talk about ergodicity. Since it's ergodic, we talk about one realization and talk about different locations of the users. This is one realization of the Poisson point process. These circles, blue circles, represent the locations of the base stations. The x, which is the grids, or the intersection of the grids, denote the location of the users. And you are asking whether what is the probability that this user is under cover, whether the received power is greater than 1 or not for this realization. Now, why is it the probability? Because you are averaging out the fading. So the one which is farther from the base station, for example, this guy, is probabilistically less under coverage. The one which is very near is probabilistically higher under coverage. Now, why the meta distribution is important? If we ask for the variation of the performance of the user across all these places, the histogram of the user probabilities, this cannot be answered only by the CCDF, because CCDF is, as we found out, that it's pi mu of x, mu of y plus pi mu of y, which gives us 0.76. It's the coverage probability, so the success probability. It gives us the average of all these numbers that we see. But the meta distribution gives us how it varies across all the users, because it is a distribution of this conditional success probability. In contrast, without the meta distribution, we don't have no information about this. The personal probability is called, and all, so you can have 0.5 coverage probability with two users, one never under coverage and one always under coverage. You can have 0.5 success probability with two users, one with 0.4 probability of coverage and one is with 0.6 probability of coverage. Okay, so we come back to the BLCP model. We are interested in the SINR, which is the signal divided by the noise is normalized, and we want to find out what is the meta distribution of SINR in this BLCP network. Again, to help us, to study some kind of metric, let's assume that you transmit with the probability P and you don't transmit with the probability 1 minus P. So instead of finding out the coverage probability or the standard success probability, we find out the probability that this SINR is greater than some gamma for a given realization of the point process, and we are interested in the distribution of this, right? So in your classical evaluation steps, so it's generally I say that you start with how you were calculating the coverage probability that the SINR is greater than something, but you stop here. Stop where you were trying to average out the point process, right? And this term, you study the moments of this. So basically, you need the distribution of this final term. But in general, a direct deriving the distribution of this is challenging. What you do is study the moments of this random variable. But it will reveal key features. So the first moment, which is the expected value of the point process of that conditional success probability, which we were historically doing, gives us back the standard success probability. But you can also now have the -1th moment, which gives us the mean local delay and variance, and you can study different aspects of the network based on how this is. Okay, so one result which was which gives us some hope to say that our model is a good one to follow is this, that when the vehicular users were moving away from the city center, and this is a real data, right? They were experiencing very poor coverage in the city center, and at the edge of the city, they were experiencing a peak, or not a peak, but a bump in the coverage. And then as they moved away, they gradually had decreased coverage and so on. As you're moving away from the city, your nearest base station is going away from you, but your interferers are also going away from you, right? What is interesting is how fast they are going away from you, right? So we have a dip. So we try to plot the expected value of D1 by D2. The dominant interferer.
You have only loss propagation or along the streets, or you have any loss also?
Both.
Okay.
Yeah. So we try to find out what is the expected value of the ratio of the nearest point to the dominant interferer distance. Lower the value of this, the better. That means with respect to the D2, you're closer than D1. So we had a deep. So this is a model which has R equal to 50. Okay, and I think different number of streets. We see that where this dip, this peak, and this kind of explains that, okay, you start from the city center, you have very close serving base station, very close interference, certain kind of coverage. You start to move away, right? Your nearest base station also starts to move away statistically, but your interferers are also moving away. But there is a point where this movement of or relative movement is the best, and beyond that, they are just moving away. I forgot to mention which kind of also. So okay, so for this the project that we were doing as a part of this work was based on vehicular telemetry services. So they just want to find out where the nearest base station is, and so that they can send very few amount of data, kb of data. They also experienced this thing that in the center you have less coverage, and at the very far from the city center you have more coverage, but near the edges you have somehow a better availability, which might well be because of the deployment. I don't know. But this is.
What is your path loss function?
Sorry?
What is the path loss function?
It's the so there is a different for line of sight propagation and non-line of sight propagation is the power law. I think, yeah. So d to the minus.
You don't take care of the singularity at zero.
Yeah, it's modified path loss.
Modified, so you take care of the singularity.
Yeah. So it's higher of 1 or d to the minus 2 for loss, and higher of 1 and d to the minus 4 for n loss. Similarly, we have the mean local delay, which is minimized for a certain transmit probability. But what is interesting is, I think not this one, but the next one is this one. So you want to find out the probability with which you should transmit so that you minimize the mean local delay. But now you should do it based on where you are located. So if you are located at the city center, you have a certain optimum transmit probability. It increases. Initially, this was a bit counterintuitive that it decreases, that when you are moving away from the city center and your interferer is also far and your base station is also far, it says that you should transmit less often, which previously we thought was counterintuitive, because if it's far, you want to transmit more often so that you have a success.
What do you mean by transmission quality? You mean that you repeat the same packet?
It's the aloha parameter.
This is aloha.
Mm.
So you take into account the collisions and so on, or
Yeah, so
take into account the fact that
via the SINR, right? If SINR is greater than some threshold, so everybody, if in an area, if you have a fixed aloha parameter, everybody follows that aloha parameter. So higher P means everybody is transmitting, P equal to 1, and P equal to 0 refers to nobody is transmitting.
so you shut down some BS with probability 1 minus P, and okay.
Yeah, and this P decreases farther from the city center, although you are far from the base station.
Why is it like this?
It's because again the speed of movement of the nearest versus the second nearest. So if everybody is far, if you increase P, the impact of interference after a while is still significant for you to have a loss, right? So you have again a peak of transmission probability at the best location. Best location means your ratio is the best of D1 by D2. And then after that, it decreases. The meta distribution gives us how much percentage of the users are getting a coverage above a certain threshold, how much percentage of the time. It's a bit convoluted. I always found this sentence a bit convoluted, but if you look back at the expression of little x and little z, you can make out that it says that certain first x fraction of the users gets a SINR minus 10 dB, greater than minus 10 dB, y fraction of the time.
So here you use the beta approximation, or
No, this is the real one.
this is the real one?
But beta approximation works perfectly in most cases. Right?
You obtain this by simulation?
This one is simulation.
This simulation. And beta distribution, beta approximation is working well.
Yeah. In general, it's I mean, I am yet to come across a paper which says that beta approximation is not a good one.
We had mixed experience.
Okay.
With this.
No, for this one it was okay.
And sometimes, even if the whole distribution looks good, when you look at the 95, I mean, for ULC, for example, problems, you have to look at the very tail, or I don't know which part, but you have to be very precise on the 999, blah, blah, blah. And here you may have some problems.
Then that is a problem, right? Because there, even if so, you see that there is
small, yes, very small.
It can mean no reliability guarantee versus actual reliability guarantee. Yeah. And no, for this one it was working well. We have that one as well, but I have to check whether so we did this beta approximation for other works as well. But as far as I have experienced, it was working okay. Okay, so I come to the end of the talk. The BLP and BLCP take into account the non-homogeneity of the Euclidean plane. Inhomogeneity in street network results in adaptation of optimal wireless protocols like transmit probability, load balancing, radar metrics such as beam width, etc. Meta distributions give us a fine-grained insight into the network. It gives us a unified framework for a variety of network properties, success probability, mean local delay. How accurate it is, we're currently working on it. One more interesting question, which I still am not able to, so we are working for it for some time, but we are not able to even start getting some good results, is the nearest point distribution in an L1 sense, which is, so for the Manhattan line Cox process, it exists. For a Poisson line process, Poisson line Cox process, so we are interested in the distribution of the distance to the nearest point while you are allowed to only travel along the roads, right? We can make ask a simpler question that you are allowed to take one turn maximum, right? So you can only go in the same street, or you can just turn once. Then things become complicated expressions, but still it's doable. But if we ask the real distribution, so you can have any number of turns as possible, we are not able to find out any results on that one. And this one remains open as a result. That let's say you are an electric vehicle and you have a certain number of distance within which you want the electric charging points, and you are only allowed to travel along the streets. So what is the probability that you will be able to cover infinite distance, right? So you travel and then. Now, how do we integrate this BLP with the existing street models is again, we are studying jointly with Professor Haenggi now. Maybe in the city center, we have more complicated structures. And then as we move out, we have more simple structures. That brings me to the end of the talk. Thank you. We can take more questions. Thank you.
For the percolation question you asked, I mean, it seems it will never percolate, right? Because I mean, you never have percolation, Poisson percolation on line, whatever the radius, right, along the straight line. And so, if you want to travel at infinity, it's just impossible, right? So, I think there should be a degenerate. I mean, for your model with a finite number of lines, right, or even if you would Poissonian it, right? So when you go far away, you see essentially lines, right? And on the line, you never percolate, right?
So in the Poisson line process,
yes,
or in the binomial line process.
So both.
So in Poisson line process, we can have so the intersection process percolates.
What do you mean?
So if you have the Poisson line process, and you are, let's say, you are saying that
the full okay, the translation invariant one.
Yeah.
Okay. But I was meaning that, I mean, you take this binomial, but you could randomize the number of points, and you get a Poisson number of points. So Poisson or binomial, I mean, would have finite number of lines.
Yeah.
And my point is that of course, this one percolates under appropriate conditions, but the binomial or the Poissonized version of it, which has a finite number, will never percolate.
Yeah. As long as the window is finite, very general, it will not percolate, because you will have, I mean, after a while, you will have straight line and
straight lines, and there nothing can happen.
Yeah. But even for the Poisson line process, let's say we don't have points in the intersections, we just have the points, right? There are, I think, I mean, of course, there are results where the percolation is defined as this one, right? So this one is nearer than within a ball of some circle. So these are connected and so on and so forth. But if we consider this distance as this one, I don't know if there are results. I don't think there are results on this one. And that's the question that we are asking.
I'm not sure. I was aware of the first one, but not.
Yeah, the first one, I mean, there has been a lot of activity in the previous years. So you have, so in Fox processes, you have the domain has to have some regularization, to borrow your word, so that you cannot be generating infinite locations of void locations. But under good conditions, the 2D distance measure based percolation, the graph percolates. But the question is this one.
With L1 distance.
Yeah. And even before, if we ask the most simplest question, like from a point, what is the distribution to the nearest point in L1 sense? It's again an open question. Okay. But for the this structure, it's known, because it becomes this Minkowski distance. Right? So if you have from here any distance, this one is either this plus this or things like that. Yeah, sorry, yes.
Next question.
Okay. This one?
Actually, the one about Here R0 is the distance of the user locations you're considering to the center.
Yes.
And P is the transmission probability of all the distance. So it means that for users far further away from the center, it benefits more from lower transmission probability.
Yeah, after a distance. I mean, so from you go from the city center, you have more and more, you have increasing in transmission, and then you decrease gradually.
Is it possible to have some location dependent transmission probability to have some sort of more uniform optimality across?
Yes. So you mean to say, is it possible to have one value of the transmission probability which is optimal for the average across all the users?
That this transmission probability P depends on the base station itself. It's not only one parameter for the whole network. So locally, if it's close to a city center, perhaps it's better to be less aggressive and perhaps better to be more frequent and further away from this.
Yeah, I think this then loses the statistical nature. So you mean to say each base station has a separate transmission probability, which you are trying to optimize, and then you average on the realizations, then you get all of them. So if you treat one base station specially, then we are then we are moving away from stochastic geometry, I think. So this P is a function of the distance. Okay. If you move further, so at a given distance, you should transmit with this probability. Okay, but all the base stations at this distance are transmitting with that probability. They don't have individual probabilities of transmissions.
So if you are given a network and you are considering, for instance, a user at 60 meters from the center, there's one optimal probability that all the stations in the network should use to optimize for the user at this location.
I see. Yeah, no. I think I now understood what you are asking. Yeah, no, I didn't think about this. So you want a probability function for a given location of the user. So if user is at 60 meters, how should for that user all the base stations should be transmitting considering where they are located and not the same across all the base stations?
Perhaps it would be some universal way to design this transmission probability that takes into account all potential user location.
Yes, I think I don't see why not. Interesting question. I have to think about this.
Maybe a bit generalization of your model can be you don't take the distance of the lines to be uniform in the interval 0 to r. You take let's say you have a distribution of the distance from the. So is it known? Is these results known for that case?
Not that I know of.
I mean, this puts an extra layer of randomness on the top, and your results can be more optimized with that putting extra randomness.
Yeah, one way to start in that direction is what Maso was saying, is to have a function, given function of the density, and then random densities. I have not thought about it, but also it's interesting.
And one more question, maybe all these results are known for Manhattan grid.
Which ones? The nearest point distance, nearest line distance, nearest L1 distance are known. Yes.
Your model makes sense for the Manhattan grid, by the way, but it's not isotropic, but it's interesting. You could have the Manhattan thing, and you would only have streets and avenues that go to east, west, north, and south. And then for a given, depending on the angle at which you look, you would have a coverage probability for an optimal P parameter.
Right.
But it would be so. Yeah. I mean, it works for any distribution of orientation.
Yeah. This is a good model for, I think, warehouses. You have a center where many robots converge, and then they have individual lanes, but not really in all directions. Maybe in some particular directions you have.
I don't see the connection between percolation and electric vehicle policies. That's nice. It's a nice way of selling percolation. That's for you, Marcel. For people aware of, cautious about environment. So that's really, so you need a policy, right? So you have to be careful as a driver to a full charge at the centers, but percolation is really the possibility of traveling far away if you obey. There is a policy of charging so that you can travel infinitely far, but not everywhere.
Yes. You can answer questions like so. Good things are that this policy can be something like this.
Better to, let's say, calculate the probability, how much the probability decays that you reach at certain distance, let's say. So that question will be a more tractable, I guess. Not the entire population question, but
so I tried to start with an easier point where on top of the Poisson line Cox process, let's say you have the intersection point process as well, right? And you have conditions under which the intersection process percolates, right? In the L1 sense, of course, because this is the distance. And then you ask questions that, okay, how far I am from another BLCP point, but if not, am I close enough to a intersection? Right, because if I can reach the intersection and that point is on top of the BLCP point, I can still say charge and go on something.
Okay, thanks again.